ever wondered why computers are so exceptionally good at recognizing human language and translating it to a different language? Well, in today's lecture we're going to find out. Welcome back to the Applied Deep Learning course. This week we're going to take a look at recurrent neural networks. But before we do that, let me quickly recap from last week's lecture. So what do we mean when we say multi-layer perceptron? Well, it's a neural network that is fully connected, where we have dense layers between each layer. So we have every neuron being connected to every other neuron of the previous layer. The key insight that we used that justifies the use of convolutional neural networks is that for images especially, we don't need the full information of all input data at the same time, but rather have information in a local area only. So in an image, nearby pixels are highly related, whereas pixels that are at the other side of the image are unlikely to be have a strong relationship. So we only use a partial connection from one layer to another. And this is the convolutional layer, and that's why it's so powerful, because it only connects local regions, therefore having a much smaller space on memory in much smaller number of connections between the neurons, and is therefore much more efficient to train. Why do we use parameter sharing and what are feature maps? So parameter sharing was to fix all weights for all neurons that are in the same layer, and the reason is that we want to recognize the same feature which one layer can learn to extract everywhere in the image. And if we only have one feature that we can extract, that wouldn't be enough. Therefore we replicate the layer, and that's what we call feature maps. So we replicate each layer d times, and then we have d feature maps. We also talked about neural networks as being feed-forward networks, where we go from the left, we have our input layer, we have a bunch of hidden units, and then we have our outputs. So last week we talked about these feed-forward networks in the context of visual computing, and we learned that they operate really well on grid-like data structure, but they have one shortcoming. Imagine a video. When you're processing a video, it can really help you to know what you did in the previous frame. But CNNs expect a grid-like structure and they can operate on sequences, but only in a limited way. So remember the YOLO video from last week? We saw that the boxes that were recognized were jumping around crazy, and the reason was that each frame was processed individually, without any information from the previous frame and without any information passing on to the next frame. So can we make this a bit better? Well, CNNs can operate on structures, on grid-like data structures as images, and you can, for example, when you have a sequence, you can work with convolutional networks here. So you have a fixed input here, for example, with 3 inputs. All of them are fed into a convolutional layer, and then you move along the sequence and you take a look at the next 3 samples, and you take a look at the next samples, and so on, until you're at the end of your sequence. And each step you produce something with your CNN. However, we have a fixed size input. So when we use a convolution like this, we always take exactly 3 samples as input. And if something crucial happened one step before that size of our input, well, we have no idea, we can't access that information. We also have a fixed size output because our convolutions are fixed, and a fixed number of computations. So the problem is that we pretty much have no understanding of previous information except for this small window that we're currently taking a look at. So when you want to translate something like the German sentence, was haben Sie heute zu Mittag gegessen, into the English sentence, what have you eaten for lunch today? Well, the problem is that the verb comes at a different position. So we need more information. We basically need the entire sequence to make some sense out of it. And we need to persist some information to capture our information that we're passing along in our sequence. We need to have kind of a state where we can access previous information for the current time step to make an educated decision. So, recurrent neural networks to the rescue. So what is a recurrent neural network? A recurrent neural network is basically a neural network that allows to have a feedback loop. In contrast to feed-forward networks, where we did not allow any neurons to have feedback loops. So what happens? We get an input X at a certain time step T. We process that, it's a chunk of our neural network, marked as A here, and then we produce an output. And that output that we produce from our neural network here, from our chunk of our neural network, is feed back into that network. So at the next time step, we can access that information from the previous step. So this graph might be a bit mysterious. How can you program something like this? Well, as with recursion, you can unroll this. And if you pick a number of repetitions that you want to, or a certain input sequence, you can actually unroll that loop. You can unfold that computational graph. So that mysterious loop is, again, basically a feed-forward network, but we unroll it multiple times. So we take the output from the first time step and we feed that into the second time step, and we feed that into the third time step. And what you can see here is that if you pass information from the first state to the second state, you can make use of that information, and at the step xt, so for the input sample xt at the time step t, we can potentially have access to the information that was processed all the way down to the very first input sample. RNNs are specified in terms of transitions from one state to another with shared weights across all time steps. So we use the same matrix and we repeat the same matrix multiplication or the same operation multiple times for each input sample. And by doing this, we actually allow the RNN to generalize to sequence lengths that it hasn't seen during training, because it doesn't matter. It will use the same values regardless if you feed it with 1 input or with 10 inputs. And it shares statistical strength across different positions. So what does that mean? We're saying that the input sequence, so when we take a look at multiple things that appear next to each other, we do not care where they happen, but we do care if they appear in a certain sequence, in a certain order. For example, I stayed at home in 2020 should be the same kind of, should allow, like the network should have the same possibility to interpret it in the same way as saying in 2020 I stayed at home, because in 2020 comes together and I stayed at home comes together. When you are now thinking of how shall we train such a thing, we are still within the same framework that we've seen in the last few lectures with backpropagation. And backpropagation, if you remember, was computing the gradient and then computing the backward step in our network to compute the partial derivatives and learn how to update each parameter here. So for recurrent neural network, this is a bit trickier because you have to actually unfold the graph to compute this backpropagation. And if you do this, we actually call this backpropagation through time. And the problem here is that we cannot parallelize this because the computation depends on the previous state. So we feed in the first value, we compute an intermediate result. The second computation actually depends on the output of the first step. So we must go through the entire graph, and it becomes really expensive to train because we have to store all of these intermediate states until they're being reused for the back prop. So when we use the shared parameters in different time steps, we actually have one assumption here, namely that the conditional probability distribution is stationary. So what does that mean? It means that we do not care where a certain sequence appears, as I just said, but the sequence is relevant that we see. So the relationship between the previous time step and the next time step is independent of the position t in our sequence. So in 2020, no matter if it appears at the beginning of the sentence or at the end of the sentence, these two things have a certain relationship. And this is the thing that we're learning, the distribution of these two words appearing next to each other. And as long as you store sufficient in your hidden state, the hidden part here where we actually capture this sort of becomes a catch-all memory, where we can pack everything in and then do a single time update step. In theory, we could also add this value t to our hidden state that we're passing along, but the problem is that the network would have to extrapolate t when facing a sequence with an unknown value of t. That's why we have this assumption of a stationary distribution here. We already have seen quite a number of activations. Actually, in the last discussion, we also talked about one more activation for convolutional networks that had some special properties. And for recurrent neural networks, we can have the same activations. However, typically we're using different activations here. So we've already seen the sigmoid activation function, but there are also like the leaky relu and relu, and something like the hyperbolic tangent function, which is actually the most common one for recurrent neural networks because it's easier to compute than the sigmoid. And we actually would like to have something that we get a bounded output between -1 and 1. Because think about the following. A recurrent neural network feeds its information back into itself. And if we have something, a linear unit that does not restrict our output in any way, that value gets fed back into the network. And unless we kind of restrict it in a different way, it will kind of explode because it gets multiplied again with a value and that value grows. And if you have multiple steps, eventually this thing will explode. That's why we typically avoid all sorts of linear units in recurrent neural networks. This thing of having the output explode actually also applies to our gradient. And this is a serious problem with recurrent neural networks. And we're talking here about two terms called vanishing gradients and exploding gradients. One would be the vanishing gradient when we propagate something through our network and we don't get any information back because the value becomes so small that we don't have any information at the first layers on how to update them. That would be a vanishing gradient. So we always want the information in the back propagation step to flow all the way through the network so we can update all parameters. The other thing would be that we have an exploding gradient where our gradient values become so large that our parameter updates just go nuts and they go into really weird values. We kind of only start to predicting extremely large numbers and then all of a sudden this thing breaks down. So when we have these gradients that are propagated through many stages, we really want them to kind of proliferate all the way down. And we have an issue here because on the one hand side, we want information to go all the way through because we want to preserve long-term dependencies. And when you think about translating a sentence, we really need to have the information. The verb, for example, in the German language is often split and it appears at the second position and at the end of a sentence. And we need to have this long-term dependency preserved. We can't forget about it. But on the other side, we must have the option, therefore, to disregard certain information. So for that information to remain in our forward pass, in our signal, we have to be able to drop other information. So some parts of the signal must have the ability to vanish, while others must be preserved. And the second problem that we have here is that when we have short-term dependencies between two words that appear next to each other in a sentence, they can have a much stronger signal, and small perturbations here can actually interfere with the signals that are coming from these long-term dependencies that naturally become less and less. So this is an issue. One question to you: why don't we have this sort of problem in feed-forward networks? Pause the video at this moment and think a few seconds why this is not such a problem in feed-forward networks. Thought about it? So the reason is that in feed-forward networks, each layer has different weights. So you multiply it with a certain number and the next layer multiplies it with a different number. So you can actually have this kind of values going up and down. Whereas for recurrent neural networks, we actually have a problem that we're using the same numbers and we're feeding it back. We're multiplying the signal repeatedly with exactly the same number. That's why these vanishing and exploding gradients are a serious issue with recurrent neural networks. So the longer the span of the dependency that we want to capture, the harder it is to actually train such a neural network because exactly of this problem. But there are special cells that can help us to mitigate this problem that we will talk about a bit later. There is one really important technique that you might encounter when you're running some existing solutions and something that you should probably use in your neural network as well, especially in your trainer, which is called gradient clipping. So we thought about this exploding gradient problem that we have these numbers that just explode and then the numbers just go crazy. So another reason why this can happen is that our error, our loss surface, our gradient can have very steep cliffs. So take a look at this image here. So we start from the left and we want to go down this cliff here, and our gradient becomes very, very large near this steep cliff. Why does it become so large? It becomes very large because the gradient here sees a really large improvement. You know, there is a really steep cliff here, so the gradient will have basically a very large value. And it's correct that it points us in this direction, but the problem is that this very large gradient might lead to taking a large step into that direction, and it can throw us completely off our cliff surface. So all of a sudden we get a really large gradient here, and then we jump to a location that we did not want to jump to. And what we can do is that we can just say, okay, if the gradient is above a certain value, for example 10, it's like a number, then we say, okay, we only take a step size up to a certain maximum of, for example, 10. And therefore this helps at least to mitigate these exploding gradients a little bit by kind of making sure that when we face these steep cliffs, where we mathematically create or mathematically have a very high gradient, not to take a too large step into a direction that throws us off. So what kind of recurrent neural networks can we have? The basically simple step would be that we have a network that is fed with one input, and then the black box that you can see in the next figures is the delay of one step. So it doesn't immediately feed it, but it will see it in the next time step. So basically we unfold this into the following. We have a so-called hidden state. Oh, I haven't defined that term yet. So basically the information that we have in our hidden units, we call the hidden state. So they have sort of the memory that we have in our network, and we start with an initial value for that, and then we feed it through our network, and with each time step we process this and we feed that hidden state to itself in the unfolded graph. We can basically have a single output at the end. So what we can do here is kind of summarize our input and digest it into one representation. So let's clear up the terminology here. So X would be our input, and that input is a sequence. So at each time step we process the next sample. We have our hidden state H, we have our target Y that we want to predict, and our actual output that comes as the last step, and a few other things. So what we have here is that the steps here actually end up with a number of steps a number of recursions that we allow the network to make. And then we have our output H tau. So that is the last state. And then we produce a certain output. And we have our target Y, and we compute the loss between our actual output and the target Y. That's our loss function. And there are three additional matrices that basically parameterize how we want to do this. The first would be U, which is a mapping from our input to the hidden representation, to the representation that the hidden units can process. We have W, which is an intermediate computation between hidden states, and a final mapping between the hidden state and the output, which we call V. So, for example, one network that we can think about where such a process would make sense if you want to read a review from Amazon and you want to say whether this is positive or negative. So you process one sequence, you digest it, and then you take one output summary of the whole thing. We can have RNNs with outputs at each step as well. So we don't necessarily have to wait until the entire sequence was processed. We can also produce something at each time step. Here you can see this kind of process where we feed back from the hidden state to itself at each time step. This is kind of the most general one, and in theory it can learn any function. It has full access to the context of the hidden state, and it can produce an output at every step or just at the end. It depends on the network what it basically can learn to do all of these things. But it's really hard to kind of make this work. So there is a second model which is similar but a little bit different. So instead of feeding the hidden state back to the hidden layer, kind of doing a feedback loop within the hidden states, we can actually have a feedback loop from the output. So the network only sees what it predicted, the output and the input. It doesn't have this kind of direct information flow from hidden state A to the next hidden state. So this is less powerful, obviously, because we're losing some information. When we predict something, we create an output, that value will be different from all of the information that we can potentially store in our hidden state. But it's easier to train, and we can actually parallelize this. And the way we can do this is by so-called teacher forcing. Teacher forcing is an interesting idea and an interesting concept how we can make this a bit more efficient. So we had our output, and that output we fed back into our hidden units that use that information to process the next time step. Well, especially during training, we might have the problem that the output that we're producing during training will unlikely be the correct thing. So we're kind of producing garbage and feeding that garbage back into our network and then expecting the network to learn something useful with that garbage. I mean, at the end, when it's fully trained, the output should be the correct output. So coming from this idea that at the end we hope that the output will be the correct output, instead of training on the output from O here, we can actually feed back the target. So we can just pretend that our network predicted the right thing, O, which is Y, and we feed that back into our hidden neurons. So during training time, we take the targets, and for test time, obviously, we switch back to our actual output. However, be careful here, because there might be an issue. When you always train on the correct output, you might have some issues here, because it's never seen the actual output. So the best would be to kind of mix this. So have some training steps where you have this teacher forcing and some training steps where you actually feed back the true output here. And now when you take a look at this unrolled thing here in the middle, the training time, you realize one thing. This is no longer depending on the previous step. Why? Because we already know the output that will, basically we know everything that is needed for time step t without computing time step t minus 1. We're not depending on O t minus 1 here, but on y t minus 1. And that is something we already know. So the good thing here is with teacher forcing, we can actually parallelize this and kind of speed up the training here for recurrent neural networks. We can also use RNNs for vectors to sequence computations, where we take one input and we kind of unpack that input into a sequence. So how does that work? We take one input X, for example, into our initial state S, kind of the initial state here, kind of H0. I think this should be just H0 here. And then we feed that through our network and we process that. So at each step, we produce a certain output, then we feed that output and the hidden computation to the next step, we produce another output, and so on until we end here. We could also say, okay, well, basically I don't want to only initialize my value at the beginning, I actually want to have that information at each time step, our input sequence here. Or we can do both. And when you think about, for example, image capturing, so we want to place a short description underneath an image, it would totally make sense to kind of get access to the image at each time step. One interesting question to you now is, how do we stop this? I mean, how does the network know if we just have one input that it should stop producing stuff? Otherwise it will just go on and say rubbish after rubbish. So there are different ways how you can do it. One would be that we say, okay, there is a special symbol that the network has the capability to generate. And whenever it generates that particular token, we stop generating. So it's kind of a terminator symbol. And how you would actually implement this is that at each sequence that you're training on, you add this terminator symbol at the end. So it becomes part of the sequence, and the network will learn that when it sees a certain sequence, it will also predict that output, that terminator signal, that token. We can have a second output head if you will, which basically represents a decision whether we should stop or not. So we produce our output that we actually want to produce, and we produce a second kind of Boolean flag that says continue or stop. And we can also say, okay, maybe we just want to have a fixed sequence here, and we can split this into saying, okay, please predict the length tau, so the number of samples that we actually want to produce here from the input, and then we just sample tau times from our thing here. Or we can do something which is quite similar, where we say, okay, we predict the number of remaining steps along our actual output. So at each step we say, okay, there are 3 more steps, 2 more steps, 1 more step, no more step, and then we also stop when this output here says please stop. We can now see that we can produce, like we can go from a sequence to a single output, from a single output to a sequence. So naturally it follows that we can also go from a sequence to a sequence. And there is a whole bunch of problems that are sequence to sequence problems. Let's take a look at the simplest case here of sequences where the input and the output sequence have the exact same length. So we take our input x t minus 1 at time step t minus 1. We have previous states or the initial state that we feed in here, and we produce our output. We can compute the loss when we compare it to the target, and we take in the next thing here. We also have this output to hidden thing here again with teacher forcing, where we feed back that to our next step, and we produce the second output, and so on and so forth. So you can repeat this, and for each input we produce one output. So the kind of model here has the ability to process the hidden state through the entire process here. So future decisions can be influenced by the state and the output here. So far, we've only seen networks that were able to access information from the past. But in some situations, we actually want to kind of access things that come after our current input to make some sense of it. So, for example, speech recognition is a great example. When you listen to interpreters, they do not immediately start translating when they are hearing something, but what they're doing is they're waiting for the person to say a few words or complete an entire sentence, because something at the end of the sequence might actually determine the information that it saw at a previous step. So it can make sense to have access to previous and future information. Now, future information is something that, if you think about it, might sound tricky, but it's actually not that hard to realize this. Because when you're training on certain data sets, we already know the entire sequence. So we can actually say, okay, go forward and go from the end to the beginning. And this is the idea of bidirectional recurrent neural networks, where we read from kind of one direction and from the other direction, therefore making access and making use of past information and future information. So we have our inputs here. We compute with 2 kind of hidden states here, H and G. Both compute something, but one of them reads from the last, kind of takes the last input first and goes to the beginning, and the other one goes forward. And then they're connected to each other and jointly produce the output. And for real-world applications, when you think about speech recognition on a mobile device, of course you can't look into the future, but you can record a sequence that is a bit longer and wait for the user to actually finish a sentence before processing it. Now, if we have this kind of sequence-to-sequence processing here, we said that we need the same size for the input as we create in the output. However, there are some situations where the input and the output might have a different length. So we want to process information that has a variable length coming in, and we actually want to produce something that has a variable length as output. And we actually already have seen how we can achieve such a thing. And it's called an encoder-decoder network. And think about it, what we did previously. So we actually have seen this before. What we're doing is that we're processing an input with a so-called encoder. So we're reading this and we're mashing everything into a context C. That was the very first recurrent neural network that we talked about, where we just produced one output from an entire input sequence. And we also saw that we can take one input and produce a sequence of variable length. So basically we just need to put these two things together, and we're creating something where we have an encoder that takes the sequence, we're processing that into the context, and then that context we're using to decode it into a variable length output. For example, when we translate words in a language, these sentences typically have a different length, so we need something like an encoder-decoder sequence-to-sequence model. So far, transitions have been quite shallow. I mean, we've seen simple matrix multiplications, but there is actually no reason why it shouldn't be a bit more complex. So we can have different models here. The first model would be that we have multiple layers of hidden units. So they influence the future, but also themselves. So we have not just one recurrency here, but we can actually have multiple things here. We can also add additional computations at various points. So we can add intermediate computations before we feed something into our network. We can have intermediate computations before we're feeding it back to itself. And of course, we can have some sort of decoding intermediate computations before we produce a certain output. For example, what would make sense here? Actually, we've seen this already. When we're processing images in a sequence, well, what would make sense here? To have something like a convolutional neural network that takes an input image, processes them, extracts information, and then goes into the, with this meaningful representation, goes into the hidden states. The last version would be that we can incorporate information that goes both directly to the next step or being based on some intermediate computations. And we can actually mix this. So one problem that we've seen and that we've talked before were these long-term dependencies between neurons, between multiple steps. And the problem is that we want information to go through, but we don't want it to explode. And Sepp Hochreiter invented or came up with one solution that is very nicely handling this problem. And they're so-called long short-term memory. So we want to have this long-term memory, but we also want to be able to not overlap with these short-term dependencies that perturbate our signal potentially. So one of the main insights that they have, that they allow us to do, is they allow us to learn long-term dependencies. So they have these self-loops, these recurrent networks. However, they make certain adaptations. So what they do is here, they introduce gates. And these gates control dynamically what information flows through our recurrent cell here and how it flows through. And the biggest change that were actually introduced was in the middle here, where you see the state, that we're using an addition instead of a multiplication. Therefore, we're allowing information to be added to the next step. And that change from a multiplication to an addition actually made this much more stable, and we can avoid this exponential explosion problem with these gradients. So how does this LSTM actually work here? what you can see here is, maybe I can point it out here. So we have our input gate that takes information, that basically is our input, and an input gate that is controlled by previous steps, which says how much information we are kind of getting in this current step. We have our state here that is being added to, and we have two more gates that are also controlled by the previous state and by potentially other inputs, which is the forget gate, which says, okay, how much of that self loop here that I'm getting here should I feed back into my state? And if the forget gate kind of says, no, you shouldn't be reading anything that came before here, kind of it will reset this, then we'll just multiply this with 0 and it won't get any information here back. When would that make sense? For example, when you're translating sentence after sentence, well, when a new sentence starts, you probably don't want to get any previously seen information here. Then finally, there is also the output gate, which controls how much output we're actually producing, how the output is being affected. So basically what this can do is that we prevent certain things from being generated, from creating an output. So that is the LSTM. There is also a similar thing called gated recurrent unit, GRU, which is similar but actually a bit simpler with fewer gates while still having a similar functionality, which is used more often than actual LSTMs. So let's take a look at RNNs in code. Again, I'm here in Google Colab, and what we can see here is another notebook where I want to kind of get into the details, into the technical details when you're processing inputs with recurrent neural networks. So first of all, you will always have 3 dimensions. And you really have to understand this to make any sense of a neural network, of a recurrent neural network. One would be the batch size, the second would be the time steps, and the input dimensions. So take a look at this image here. So if we have 3, 4, and 5 for batch size, time steps, and input dimensions respectively, we would say that we process 3 observations at once. That's our batch size. So we kind of take 3 sentences that we're processing together. We can just process one sentence, but we can also have multiple batches of multiple sequences where each observation is described by a sequence of 4 values. Basically saying that each sentence will have exactly 4 words or less. So a maximum of 4 values. And each value in our sequence is being represented by 5 features. So it can have 5 numbers to represent a single word or other information. So for word translation, we would actually map this to just one number. So we would have just one feature. But think about it here. So we have the batch size, which would be kind of the width here. We have the time steps along here. So we say that we have a certain sequence length, and each observation here has a certain number of features. Now, let's take a look how we actually implement this. We can say the batch size is 3, sequence length 4, or the number of time steps here would be 4, and the input dimension number of features is 5. We also say that the number of features in our hidden state is 6, so that's the number of digits that represent our internal state. So we can have 6 numbers that we're passing along through our hidden units, and we're stacking 2 layers behind each other. We're saying the number of layers should be 2. And then we feed all of that into a recurrent neural network here with PyTorch, and when we produce an input of that shape, so we'd say batch size times sequence length times number of input features, that's our input. We also generate our hidden state, which has to have the number of layers, because for each layer it has to have the parameters, sequence length, and number of features in the hidden state. We can actually apply this here, the recurrent layer, with our input on that hidden state, on the initial hidden state H0, and what we get here is this. So we get a tensor of certain dimensions here, so it should be a 5 by 4 by 3 tensor, right? So we have 3 samples here, like a batch of 3 kind of chunks, and for each chunk we have a sequence length of 5 samples for a sequence of 4. Yeah, so there you go. You can do the same here with Keras. Keras defines it a little bit differently, but if you understood the basic concept, you will grasp how Keras does this as well. So we say simple RNN, a simple recurrent neural network with the number of features in our hidden state. So that was 6 before, so let's go again with 6. We also say return sequences because our output is not just a single value, but also a vector. And then we can also build this recurrent neural network with these batch size, number of input features, and the sequence length. So let's take a look at a bit more complex model here in Keras. What we're doing here is that we're saying, okay, our input here is an image. So we process that image in a certain way and extract some meaningful representation of that image. So we're using a convolutional network here as our input encoding. And then when we extracted a certain number of features here, that's our inner, we are reshaping this, basically flattening our features the same way that we've seen last week. And then we kind of process this in a dense layer to kind of make some sense out of it, to allow the network to kind of cut down the input size before we go into the recurrent neural network, to have a fixed number of outputs, because dense layer can have an arbitrary number of inputs, but it always produces a certain number of output neurons that we're calling here time dense size. So time dense size is 32. So each recurrent layer here, our gated recurrent unit, is being fed a vector of 32 inputs. And what you can see here is a bidirectional network where we have 1 and 1b, one going from the inner thing here and the other one going backwards here. So by saying go backwards, it kind of processes the sequence in the opposite way. Then we add them, both of them, to each other. And that merged value we feed to the next layer. So we're kind of having these intermediate connections between the gated units. And at the end, we put them together. We concatenate the two outputs from the second gated recurrent unit. We feed it into our last dense layer, and then have an activation function to produce a softmax output, an actual probability distribution that we can process, which will be the encoding of the letter that we're using. And there's one final thing here, which is this weird CTC lambda function, but I'll come to that a little bit later. So that's our network. When you take a look at this, at the summary, you can see that we're processing this here in the convolutional layers, and that these recurrent neural networks actually have lots of parameters here. So this one here has 1.5 million parameters already. So it is actually really can be quite challenging and demanding to compute something here, to train this network. That was the first simple example of recurrent neural networks that we can use to do something useful. But there are tons of other applications that we're going to take a look at now. The first thing would be to make some short-term predictions. So we can kind of have an input sequence, a waveform or something, and we want to make short-term predictions. We only take kind of a look at the first few examples that came along and then do something with it. So let's take a look at this. Okay, we're back here in our notebooks, and what we can see here is that basically we're generating some data here initially and adding some nice graph visualization functions here. For example here, so we're basically just creating some fake data set which has certain regularity and that we want to process. And what we can do now is that we kind of have different waveforms here, and when we're training now, we're only taking a look at a certain number of samples of a certain window size. So we're preparing this network here, we shuffle our data sequence. I'm not going to go into the details of all of the commands. Feel free to click on the link in the presentation and play around with this notebook yourself. But what we can do here now is that we kind of peek at the data, and here is the model that we're actually using here. So we're reshaping our input here with a certain sequence length. So we can have, for example, 10 input elements. So what is our sequence length? Let's take a look at this before. So sequence length is 16 samples that we're taking a look at the same time. We feed that into a convolutional layer, into a one-dimensional convolutional layer with 8 filters, and then 2 more layers, and so on and so forth. And at the end here, we compile the sequential model. Blah, blah, blah. Where is it? Model layers from lambda. Ah, there you are. So here is the function model layers from lambda. So what we're doing is that we're specifying our own lambda function that is an anonymous method that we're applying on our input. And what is that lambda? We say model layer random, last 2 linear. So these layers, where were they defined? Oh, they're still here. Predict random values, same as last value, trend from last 2 values. So those are 3 different functions here. So we're saying predict same as last value. So that would be our benchmark. Say, okay, give me the same that the last thing was, predict the trend from the last 2 values, or do something else here where we are benchmarking model 3 with some random values. What do we get here at the end? We have a neural network that is basically just using convolutions and sort of feed-forward network here, and let's see how good it works. So it's not exceptionally good. It says here 0.18%. So instead of just having a fixed number of inputs here with our thing, we can actually have an RNN here, where we say use a gated recurrent unit instead, and we can also train this here, blah, blah, blah. There you go. And yeah, so we get a loss that is 0.02 as opposed to what loss that we get here, 0.03. So we have a bit better network here with 2 recurrent neural networks. Here we had like a root mean squared error of 0.18, and here we can actually see 0.16. So it's a bit better, and this is what our network can do. This is a nice visualization of what our network predicts and what the actual ground truth would be. And as you can see here with these simple models where we just have 2 gated recurrent units here, for example, here, oops, sorry, here, we can actually already do this kind of short-term modeling in a really nice way. We can also use CNNs and recurrent neural networks together for optical character recognition that we've already seen in this small example before. But let's visualize it and conceptually think about it once more. So we have an input image and we want to translate that. So how would we do this? Well, we could actually do something where we take the input image, we extract some features in a meaningful way, and then we reshape this. We put it in the dense layer, and then feed it into our recurrent neural network. So what it does is that here we process our text line by line. So we start with a small input window here that extracts features from the image, and we move that sliding window here along the x-axis. And then we use a so-called best path decoder, because there might be repetitions and other things that are in our output that we need to decode here to actually obtain the correct recognition from our input image. And this idea of taking an image, extracting some features, reshaping it, and then feeding it into a recurrent neural network, you will see is a common pattern. For example, for recognizing music scores, one of the approaches that have been explored in recent research is that you take an entire stave of music scores, where you have all the scores, and you apply the same idea again. So you basically have this window that slides over the network, and you extract features for each of your window slices, and you feed that into an LSTM or a gated recurrent neural network. You produce predictions, and that kind of should be your translation. So for this example here, I mean, it's flipped now, but you can see a G clef here, and then certain key signatures, time signatures, and then the actual notes. And the network learns to predict this sequence from that image. Image captioning is similar to what we've seen before, but we're not just producing a summary, but we're producing a sequence as an output. So we want to have somewhat an encoder-decoder scheme, but our encoder here is a convolutional neural network. In this case, it's a quite complex convolutional neural network, but again, we extract features from our input image, we feed that into an LSTM, and then we process it step by step. Speech recognition can also be done with recurrent neural networks, as you can imagine. We've already seen this simple sequence modeling example before. It turns out that people from the audio domain borrowed some ideas from the guys from the visual domain, and what they're doing is that they're translating an audio signal into an image. So what they're doing is they're extracting the MEL spectrogram from the input audio, and once we have an image, we're feeding that image into a convolutional neural network, and from there it's the same thing that you've seen before. So we're extracting features with the convolutional network, feeding them into the recurrent neural network, and then predicting something. So the MEL spectrum, if you've never heard before, is basically taking the waveform, cutting it into chunks, and perform a fast Fourier transformation. And we separate the frequency spectrum into evenly spaced buckets according to the human ear. So we're kind of generating this spectrogram, but in a meaningful way, in a kind of human meaningful way. Because otherwise we will always have, like when we are speaking, we're always speaking in a certain frequency range. So frequencies between 10 and 20 kilohertz would never see anything. That's why we're taking this MEL spectrogram to have an evenly sized bucket thing here to get kind of a more focused look at things that are relevant for speech recognition. Features basically here. So speech recognition now becomes something like this. That's one way of how you can do speech recognition in a really kind of standard way, I would almost say today. And by now you should start to be able to read diagrams like this. So what happens here? We're seeing our input that is being fed into our MEL spectrogram preprocessor that converts our input sequence into a convolutional, into something which is kind of an image that we're feeding into our convolutional layers in the middle. We're squeezing that together and then feeding that into our recurrent neural network. In this case, a bidirectional LSTM. that has some additional mechanisms potentially to make sure that it kind of looks at the right parts of the input that it came before. And then at the end, if we do some classification, we have a bunch of dense layers where we produce our actual output. So there's one thing I already mentioned before, which is the so-called CTC, connectionist temporal classification loss. And the big question is, how do we handle unaligned data? So we have two modalities. One would be the waveform, and we have the transcription of that waveform, which is, my friend has too many cats, like this. So the question is, how do we align them? CTC allows us to do alignment-free training here. So we only need the input sequence and the second sequence that we want to produce as output. So how does it work? We're summing over the probabilities of all possible alignments between the input and the target and our label. This sounds maybe a little bit over the top and especially really expensive, but when you visualize it, you realize it's not that bad. So we're going back to the image domain here and think about the image that you can see at the top here, AB. And we have a sliding window, the red rectangles that we're moving in each time step one step forward. So at the first time step, we get a certain output probability distribution, which is kind of the output of our softmax. So we say the highest chance of what we're seeing in that window is an A. Now we move to the next window. Again, the output predicts, the network says, well, this is probably an A. Again, an A, then maybe a space, a blank, and at the end, something like a B. So those are the probabilities, and how it can say this is by taking a look at all of the output probabilities and just taking the maximum value at each time step. Basically, what we're doing here is we're aligning them in the most probable way. We're saying what is the most likely combination here of this sequence. For audio, think back of the sentence, has too many cats, which some people would say is not possible. We would generate something like HHAS blank TTO, and then we also have something really interesting here, the epsilon, because the CTC output here would actually contract repetitions into a single unit. So HH would become a single H. AS would be translated as AS. Again, TT would be contracted. So if we have the same output appearing next to each other, they all get squashed into one output. And if we have the same output value appearing twice next to each other, we have to separate it. That's why the network is typically also able to produce something like an epsilon, which is a separator character. So in this case, to produce the output OO, it will predict this separator character in between here. So, summing up, recurrent neural networks have feedback loops as opposed to feed-forward networks, and therefore have the capability to store state information and reuse that in the next time step. They're ideal to process sequential data where this memory of previous information is beneficial. They can be trained with backpropagation through time, which is basically just backpropagation on the unfolded computational graph. They're harder to train than feed-forward networks because we're using the same values over and over again on the same input, on the same values. And therefore, we can have the problem of vanishing or exploding gradients. And they have the capability to process arbitrary input and output sequences of arbitrary length. And to kind of combat some of these vanishing and exploding gradient problems, there are some ideas of special cells, special kind of ways how to construct a neuron, so it's not just a single multiplication and adding a bias term, but it's something more complex. One example would be the LSTM cell that do allow us to handle long-term dependencies between multiple input sequences. And basically what they do is replace the multiplication with an addition, and therefore allow us to also process sequences that are longer, where you have a relationship between a word that appears at the beginning of the sentence and at the end. And last but not least, CNNs and RNNs play really well together to solve challenging problems, as you've seen before with optical character recognition, music recognition, or even some sort of speech recognition. You can actually formulate this as an image recognition and then sequence understanding problem. Hope to see you all next week. Stay healthy and have a nice week.